Hello, good morning, good afternoon, and good evening, wherever you are, and welcome to the Synchronization and Timing Self-Paced Bootcamp. My name's Dennis Haggerty. I'm a technical marketing engineer. I work for Cisco Systems in what's called the Service Provider Access Group. Now we're responsible for access products which are out at the edge of the network, and most of our customer base is service providers, so like large mobile and fixed wireline networking companies, service provider to customers. So what we're going to cover is we have put together a three-part series explaining timing and synchronization. It's bigger to be a little like an overview or like a training course, if you like. We called it sort of Sync and Timing 101. It comes in three parts. Part 1, we covered the basic concepts of timing and synchronization. So we covered, frequency synchronization, why we need to do it, who's interested in doing it, how we do it, how we measure the quality of it, and we then touched on time and phase synchronization. So if you really need to understand the concepts behind clocking and synchronization, or find yourself falling a little bit behind, then it's best to go back and look at part 1, which will give you a good grounding of all the basics. This session is part 2, and in part 2 we're going to talk about packet-based timing, and that basically falls down to talking about IEEE 1588 or PTP, and we're going to talk about the various clock types. We're going to have a look at the protocol. We're going to talk about how we get time and phase information into the 1588 nodes and how we get it out. We're also going to talk about a concept in PTP called PTP profiles, and we'll go through some deployment considerations. So where it's deployed, what machines in our business unit portfolio support various features in PTP. And the next part 3, was where we will actually go through and show you how to configure each of these. So what's supported, what's not supported, and we'll go through then each of the options that you need to configure for both TDM, for SyncE, for PTP, for frequency, for phase. The lot will be in part 3. But this is part 2, and we'll be covering mostly 1588 and PTP. So this should go for just over an hour, hopefully. The last one that I did in part 1, I thought it would go for an hour and a half, and it went for 2 1/4. So please bear with me, but you can pause at any time and come back to it. As I said, see part 1 for an introduction if you need to understand the concepts behind synchronization and timing. So firstly, we're going to have an overview of what is IEEE 1588. So as you might imagine, IEEE is a standards organization. So 1588, 2008, is the nomenclature of a standard. It's the name of a standard for a precision protocol for networking together management and control systems, and industrial, mainly in an industrial application. So it consists of various parts. So let me take a step back. IEEE is the standard. The standard defines a protocol. The protocol is what's called PTP. So if you hear people referring to PTP, people turn to 1588, people referring to PTP version 2, then that's pretty much talking about all the same thing. It's defined under IEEE 1588. 2008 is the last standard. Now PTP is like NTP. It's a two-way time transfer protocol, and we'll explain what that is in a minute. So I explained in the first part that there's a little difference between PTP and NTP. NTP, it really is only about, for most common implementations of NTP, is about being able to give time of day, and it's typically used for things like, your PCs and your smartphones to be able to get time from the network. PTP takes that to the next level, And it was originally specified because people required much better accuracy than was available in NTP. Most NTP implementations are not able to give you a level of accuracy beyond, below milliseconds at best, and quite a few implementations quite a bit worse. But 1588 was looking at going sub-microsecond, so into the nanosecond range, for being able to do, for the precision and accuracy for the time that it can transfer. What PTP is also able to do, it is able to do transfer as well as phase and time synchronization. It is able to transmit frequency. So this is of importance to telecom service providers who want to get away from having a physical frequency distribution network because they don't have the circuits to a particular location because of its remoteness. Then what they would like to do is to, if you like, collapse all their networks down onto one, so that they can run their data networks, they can run all their synchronization needs, and they can run it all over a packet-based network. So 1588 gives us the ability to carry frequency, phase, and time sync with packet-based technologies. And as I said, this is of interest to a lot of telecom service providers in particular. They're not the only ones. There's quite a few other applications and industries using it, but there's certainly they're the ones who've stepped forward in the last couple of years and have shown the most interest. Basically, administration-free operation, which of course is a promise everybody makes. But really, it doesn't require an onerous amount of administration, and it's meant to be, self-managing and self-healing. And you'll see as you go through how we do that. It's also designed to be both for high-end devices, which is easy to do if you've got plenty of money and you can afford to over-engineer. But 1588 was also designed to go into low-cost, low-end devices, especially for industrial applications. And as we said, when you're collapsing all your, say you're backhauling traffic to and from a cell site, or you're collapsing all your corporate network onto a single packet-based network, you need an in-band solution, and that's what PTP does. So you don't require a separate clocking network for your synchronization needs. The packet data can flow over your standard packet network. So there were a couple of versions of 1588. The first one was IEEE 1588, the version 1 standard, was mainly designed about supporting timing in an industrial automation environment. And so it was designed about enabling accurate time transfer in the sort of an industrial industrial context. With 2008, we got a second version, and that added features for WAN deployment, and also introduced the concept of a profile. And what the profile really means is that it allows you to pick subsets, to redefine certain portions of the standard, and limit it, if you like. So it sort of can be a superset and a subset to say this is the subset of this complete standard that we need for this particular use. So what it does is it allows you to simplify your deployments. You could say, well, we're only supporting a particular subset, of messages or of data fields, and it can be tuned to a particular problem you're trying to solve. A couple of examples you'll see. I'll give more information as we go through this, but the first one is G80.265.1, which is a profile being defined by the ITU, and that's really to address applications where you only need frequency sync. So you're using PTP packet-based network, but you're only interested in recovering frequency, and you don't have something like TDM or SyncE to do it. So that's been defined to solve that problem. There's also recently been ratified 8275.1, and that's for mainly telecom applications, but it's for where they require accurate phase and time sync as well as frequency. And the most typical use case for this, which 8275.1 was defined for, was for 4G networks where you need phase and we'll go through these use cases in a while. But it's possible to define other profiles as well, and quite a few of them are under study, and to solve different problems with phase and sync. And the extra colon comes free. So first we're going to talk about clock types. So we've got a few concepts to define in PTP, and the first form of a clock that we really have to deal with is what's called an ordinary clock. And ordinary clocks come in two flavors. There is an ordinary master clock and there is an ordinary slave clock. So these are the terms from the standard, so you'll see these used everywhere. It's much like a client server. The master is the server and the slave is the client. The master is typically uses a reference source, and it will take in timing, clocking information from typically a GPS receiver. It takes in various pieces of information, normally 3. It'll take in a frequency source, which you can see there indicated by a purple square wave, which call a primary reference clock, depending on your nomenclature, and I talked about that in the first part. And then it takes in phase and time of day for what's called a primary reference time clock, or a PRTC. So this ordinary master then uses that to generate PTP, a packet stream, and sends timing information. It's actually a two-way protocol, but I've used the blue arrow there to indicate timing information rather than packet stream, because the packet stream is two-way. And that then goes to a slave clock, an ordinary slave clock, and the ordinary slave clock is defined negotiates to talk to the master, and then it uses the packet stream to recover the clock, which we explained in part 1, and it can then recover the frequency information, use it to condition its own oscillator, and then it can use that timing for any downstream equipment that requires frequency. But it is also able to provide time of day information and phase information as well. So you recover both frequency and time. Then we introduce the concept of a boundary clock, and what a boundary clock does is it sits in the middle, if you like, and whereby it is connected. It has 2 ports. One's a slave port, one's a master port. And what happens is the information from the master to the slave sets up a PTP session, and the slave recovers the clock for that device, for that network element, and then uses it to condition its own oscillator and set its own time. And then you have a master, a different PTP port they call it, which is a master, and then that can drive downstream slaves. So a boundary clock, if you like, is a way of demarcating between 2 different PTP streams. Of course, a boundary clock can also just pass PTP traffic straight through. I mean, it can obviously normally it's an IP packet stream, so it can pass it straight through. The difference between an ordinary clock and a boundary clock is that an ordinary master is either a master or a slave. It doesn't change. Boundary clocks can be a bit more flexible. It depends on the profile, but a boundary clock can actually works very well in ring environments, because it can change between the master and the slave. So if a slave loses connection to a master, you could actually send traffic around the ring in the other direction by having the slaves turn to masters and the masters turn to rings. Similar things happen with synchronous Ethernet in a ring as well. So boundary clocks in standard 1588 can actually swap between slave and a master port under control of the PTP stack. But normally it does not for ordinary clocks. Once a slave is a slave, once a master is a master. One other benefit of a boundary clock, of course, is in those environments where you're not using a routed protocol to carry PTP. So for instance, you're using Ethernet or some layer 2 mechanism to map your PTP traffic. A boundary clock is a way of being able to recover clock in one, say, a broadcast domain, and then being able to pass PTP on in a different broadcast domain. So these are quite widely used in industrial applications, especially where you're using layer 2 transport. Boundary clocks also are used to correct delay variations, clean up noise. We covered this a little in part 1. Where we use like SSUs to clean up noise and jitter in the network. Well, boundary clocks also perform a similar function in a packet-based network. And the last one is a transparent clock. Transparent clocks come in 2 flavors, but in general what they are is it's a way of being able to take account of the amount of transit time that you spent in the network, and what it does is it corrects for the amount of time that the PTP packets have spent in a network element, and then it is able to correct that on the slave. I'll show you the details of that in a little moment, but just at the moment we're just covering the whole clock type. So we have ordinary master, ordinary slave, a boundary clock, and a transparent clock. One thing I also should point out about transparent clocks as well is there are various types, but the most common transparent clock you see, it doesn't participate in the PTP stream. It doesn't have a stack, if you like. It doesn't really understand a PTP, so it doesn't have any stack or servo inside it which is interacting with the PTP stream. It purely uses a mechanism to timestamp packets as it goes through. So the sort of fundamental difference is that boundary clock understands PTP and interacts, and transparent clock really doesn't. So how does PTP perform this miracle? Well, really the secret sauce behind it all is using of timestamping, and hardware timestamping is preferred. And the idea is that as the packets leave the master, they can be time-stamped as close to the packet going out on the wire as possible. And so a lot of this then comes down to the design of the actual hardware, but more and more devices now are made with this in mind, that you need to do time-stamping. Of course, NTP now does similar time-stamping, Y1731. There are more and more mechanisms that are using this to try and ensure the quality of their time stamping, but this is really the secret behind it. So I talked a little bit about boundary clocks. We'll dig a little bit further into it. So as I said, we have a master clock, we have a boundary clock which is a slave to a master clock. When that element, the boundary clock, recovers its time and its frequency, it uses condition its own oscillators, update its own sets device. Then it has another PTP stack running, and that is then the master stack, and it then generates another packet stream for all the downstream slaves. So as a boundary clock has at least 2 PTP ports, it has a slave and a master. You can have multiple slaves, and you could actually have multiple masters. As I've said, it is used to clean up jitter. It's also to reduce node latency and asymmetry. So for instance, if you have a node that has a very high latency, if you can make it a boundary clock, you actually take the latency out of the equation, because there's no packets transiting through the boundary clock. The slave is recovering time and frequency, and the master is distributing it. So it's a good way if you have a node with very high latency. As I said, it's useful when it has when you don't have a routed protocol. For the example is Ethernet. Cisco makes industrial switches, and they use Ethernet multicast, and in an industrial environment you would actually set PTP being multicast down. You would have a boundary clock, or if you're doing unicast, you'd have a boundary clock slave, and then you flood it out of one bridge domain into the other, or one broadcast domain into the other. Another clock type I should just talk about is what's called a hybrid clock, because it's becoming more topical over the last year. And a hybrid clock is a little bit of a mixture. whereby you use a boundary clock or a slave, but you only use PTP to recover time and phase. PTP is not used to recover frequency. So let's have a look at our example here. I'll get my trusty pen out. So we have an ordinary master and we have a frequency source. So we have like a atomic clock or a GPS source, and we have a primary reference clock which is giving us time of day and phase. And the ordinary master is generating a packet stream of PTP packets. Of course there's some coming back in the other direction, but in general the timing information is flowing to the right. So here we have configured a hybrid slave. Again, it's just a simple configuration option, but it only takes the packet stream in to recover time and phase. We actually use an external reference clock, and this can be another GPS receiver like we have on the master clock, or it could be something as simple as SyncE. Now of course this SyncE can come from external, or it could actually flow over the same link that has brought the PTP packet in. So what you're doing is you're using a packet-based distribution mechanism to distribute time and phase, but you're using a physical distribution method to distribute frequency. Typically it's SyncE, but it can be any other frequency source. So I should actually show here that you have two options. You have an out-of-band options where frequency comes in from another SyncE port or from bits, or you actually get SyncE from the master over the same link that you receive the PTP packets. Now this gives you a really great advantage, and specifically when you get things like going into holdover. Holdover, if we lose connectivity to the PTP, say for some reason we've lost connectivity to the PTP master, but we still have our frequency reference, so we still have SyncE available, then because the frequency is so stable, the phase can't move. This is like I explained in part 1. If you are driving down a road and you're 100 meters behind the car in front, then you're doing the same speed. Conversely, if you're both doing the same speed, you don't get any closer or further away. So the frequency is the way of saying, well, we're doing the same speed. I'm doing 100 kilometers an hour. The car in front's doing 100 kilometers an hour. As long as you keep exactly to that frequency, then you'll not catch the car in front. So it gives us very good holdover performance, and more people are starting to go down this route of adopting a hybrid, or what we call a hybrid mode. Details of transparent clocks. They are a little bit complicated, but the good thing is we can ignore most of them. There's really two types of transparent clock. The one that we're most have to worry about is the end-to-end transparent clock. And the end-to-end transparent clock is where I said the transparent clock really doesn't get involved at all in PTP. It purely does time stamping. So what it does is, as a PTP packet goes through a node, so it's not a master clock, it's not a slave clock, it's not a boundary clock, it's purely forwarding packets, in some Ethernet or some IP network. It's forwarding packets, and what it does is it measures the amount of time that the message was inside the device, and it updates a field so that the slave can take account of it. And we'll give a bit more detail in a minute. But just so you know, there's another one called a peer-to-peer transparent clock, and in a peer-to-peer transparent clock, the transparent clocks actually understand PTP, and there's actually messages running backwards and forwards between them. And that can be used for measuring things like link delay between ports and so forth. So there are some uses for it, but normally you don't see them. Transparent clocks, I said they can be one-step or two-step. We talk about one-step or two-step in a moment, but basically for end-to-end transparent clocks, they just pass on the PTP packets that are going through them, so you don't have to worry about that too much either. So in general, we support the end-to-end transparent clocks. So this is basically how it works. This is an end-to-end transparent clock. We're showing a packet go through a network element. Now the network element is not a PTP element. It doesn't understand what's going on, but it does know enough to see a PTP packet when it sees one. And basically what it does is it figures out the amount of time that it's inside the network element, and it updates a field which tells the slave how long the packet spent in that transparent clock, so that the slave is able to take that time out of the calculation for delay. So we'll show you how it works a little bit in a moment, but this is basically what it does. It's purely figuring out how long does the packet take to go through this device, and updates a field so the slave can take account of it. So here we're showing with an end-to-end transparent clock a simplified, although it mightn't look that simplified, but the way that this two-way transfer protocol works is that you are passing timestamps backwards and forwards between the master and the slave. So we'll spend a little minute on this to explain how this all works. So here we have on our left-hand side we have a master clock with its reference, and on the right-hand side we have a slave clock, and we've put a couple of simple ladder diagrams in here to explain how the process for an end-to-end transparent clock works. So the master sends out its basic message, which we'll cover the messages in a minute, but the most basic message it sends out is a sync message, and it contains a timestamp of when it was sent from the master. Now this sync gets received at the slave, and so the slave then can determine the fact that there was a time when this packet was sent and the time that the packet was received. However, of course, there's two problems. And problem number one, of course, is that this master and the slave's clock might not be the same time, so there's what's called an offset. And the second thing is you don't know how long it took the packet to get from the master to the slave. So what the transparent clock does while you're doing this is, as the packet passes through the transparent clock, which is this piece here, it determines the residency time of that packet in that device. And so it is able to take and basically, if you want, completely eliminate any variation that happened in the transparent clock. If you could imagine that the transparent clock took a longer period of time, the residency time was longer, then you get packet delay variation. However, the first packet is going to say it stayed in there for RT1, and the next packet it stayed for RT2. So the slave will have a very good idea of how long each particular packet spent in nodes that are between the master and the slave. So it's a very good mechanism for doing this. Similarly, in the other direction, when you set it to two-way protocol, the slave sends a message back to the master. So the slave here knows how long it thinks it took to get from T1 to T2, but what it has to do is it has to determine what's the round time trip delay. So it knows that how much of the time it's different was spent in transit and how much indicates a difference in the clock. So there's two pieces of information it needs. It needs to know what's the round time delay, and then it can determine what the clock offset is and correct for it. So to do this, it needs to send another packet out to the master, which is basically asking for a delay, and similarly they use timestamps to calculate that, and we'll show you how that's done in a second. But just for the point here, we're talking about transparent clock. Similar mechanisms happen in the other direction, so that the master is able to determine that the residency time of the packet spent in the transparent clock, updates this field so that when the master receives the packet, it is able to take account in its calculation of the transparent clock and remove the effect of the delay of the packet in transiting that transparent clock device. So it's quite a powerful mechanism. Of course, to do it, you need basically hardware support to do it with the time stamping, and then you need to understand the packets so that you can activate the time stamper. So that really covers the different clock types. So moving now to the actual protocol itself. So what are the messages and what gets transmitted between the devices? We've already had a little bit of an introduction with sync and delay request. So I realize this might be a little bit overwhelming, but if I go through it once, there's plenty of references on the internet you can use that give basically the same information. And if you come back and listen to it again, then maybe it'll sink in better the second time. But just so you know, there's different sets of messages in PTP, and not all of them are necessarily used in any particular implementation or profile. So we have what's called event messages, and event messages down the left hand side consist of these. Mainly the first two are the most important, and the sync and delay request. What is an event message? An event message is a message that requires timestamps. So all of those four messages require timestamps. As I said before, transparent clock peer-to-peer understand PTP and they send messages to each other. So as you sort of understand from the name peer-to-peer, they talk to each other, and this is the packet types that are used to talk between peer-to-peer transparent clocks. Now, as I said, we don't deal with them too much, so I'm not going to talk about them too much. On the right hand side, we have what's called the general messages. And general messages do not require timestamps. Similarly, there's a couple of very common packet types that we deal with, the follow-up and the delay response. There's another set of packet types for peer-to-peer, which we won't talk about. And then there's some special ones, which are things like announce, where the packet master declares, it's what features it has and what quality it has. We have signaling messages where negotiation can go on between the slave and the master. And there's, of course, as you'd expect, there's a number of management messages as well to be able to control the PTP flow between the master and the slave. Now these messages can be mapped onto various types of into various frames. Possible ones are at the moment layer 2 Ethernet, IPv4, IPv6 with UDP. There's an MPLS encapsulation. So if you look at the IEEE 1588 standard, there's a number of annexes, and the annexes define the mappings to possible protocol types. Now, all implementations and profiles tend to restrict that to a subset of those. So just because you don't support a particular form of mapping does not mean that it won't work for your application. Then there's transmission modes. They can be either unicast or multicast, or some mixture of the two even. They can be multicast in one direction and unicast in the other. We will go through the profiles in which are unicast and which are multicast a little bit later. Again, it's specified by the profile. And then within that, there's a whole slew of TLVs where you can define particular data types that are passed between the slave and the client. Also, they are restricted or defined by the profiles, so that there can be different interpretations of TLVs or different fields. As well as that, there's a lot of information flowing about the rates at which some of these packets are sent, what the timeouts for some of the packets can be, how long before you declare that you've lost the master, how many missed packets can you handle, that sort of thing. So as you sort of expect from a dynamic protocol, and that's all defined in the IEEE 1588 standard. So now we'll just take a little minute to understand basically how it works. Now this might take a little while to get your head around, so I don't expect you to get it the first time, but it's actually a fairly straightforward mechanism of determining the clock offset between the master and the slave, and we touched on it a little bit when we talked about transparent clock, but here we're going to see in detail exactly how this works. So first, on the left hand side of the ladder diagram, here we have a master and the master clock, and on the right hand side we have the slave clock. Now the slave, the time on the slave is the time on the master plus some offset. Well, like, that's obvious, the clocks, even if the offset is 0, but the clocks would almost never be 0. The time on the slave and the time on the master are different. That's all that line says. So here you know that there's an offset between the slave and the master. So what happens is the master sends out a packet, and the packet is called the sync packet, and it records the time T1 at which it sent the sync packet out. Now that T1 actually corresponds to a different time on the slave, so because there's a difference, when it sent the packet it was here, not here. So you've always got to remember there's this offset, and that's what we're trying to reduce to 0 so that the clocks are synchronized. The sync packet arrives and the slave records the time at which that packet arrived, T2. And what happens is the master doesn't actually send that T1 in that sync packet. It depends, it's what's called a one-step or a two-step. In this case, we get a follow-up message. It's a two-step, so it actually sends the T1 in this packet. As you can see there, the follow-up message contains T1. So at this point, the slave knew T2 when it's received. Now when it gets a follow-up message, it's got T1 and T2. So it actually knows when the packet was sent according to the master, and it knows when the packet was received according to the slave. So with just simple maths, you can say, well, we know that the difference between those two, so when I received it and when it was sent, consists of the offset between our clocks, obviously if the clocks are different, and the delay. So if the delay was 0, then the offset would indicate the difference between the clocks. So if you sent me a message at at 12:01 and I got it at 12:01, and the delay for me to get the message was 0, then obviously our clocks have not got an offset, they're the same. So it immediately knows that the offset and the delay is the difference between those two numbers. So offset is what we need to know. We need to know how far our clocks are offset, so it has to determine the delay. And the way that it does that is it takes the round time trip between the master and the slave and it divides it by 2. So you can see down the bottom here, that's really what this equation is telling us. So it's going to say what is the round time delay between master and slave and back, and divide it by 2. But we don't have that information yet. We only have the one-way time. We know the offset and the delay, but we don't know how much is which. So what it's going to do is figure out the delay, and for that you're going to take the round time trip divided by 2. So what it does is it sends out another packet called a delay request packet, and it timestamps it with T3 when it sends it. The master, when it receives that, responds and sends back T4. So at this point the slave, when it sends a packet, knows T1, T2, T3, and when it receives the response back, it knows what T4 is. So by doing that, it knows what the round time trip delay is. So it can actually, by using T2 minus T1 with a bit of simple arithmetic, can then calculate the delay. But in general terms, the delay is just, all it's done is calculate half the round time trip. And then because it knows the delay, it can calculate the offset because it knows all the rest of the information. So this, then the slave knows what the delay is for the packets taking to get to it, and it knows what the offset is, so it can then condition its oscillator to make the offset 0, so basically to synchronize the slave clock with the master clock. And that's pretty much how the process works at its simplest form. One thing I should point out is this is why I said in part 1 that packet-based clock recovery mechanisms do not like asymmetry. And of course you can see now why the asymmetry is a problem, because it assumes, and it has no other way of doing this, that the delay is exactly the half of the round time trip. So this means the trip from the master to the slave is the same as the slave to the master. So if a packet takes 50 microseconds, for just come up with a number, then it assumes that the master is 25 microseconds away. If it's 40 in one direction and 10 in the other, then you have a problem, because the slave will think that it's that it's 25 microseconds away, when in fact it's only 10 in one direction and it's 40 in the other. So it will get the clock calculations wrong. So this is really why asymmetry is a big problem for packet-based recovery mechanisms. Okay, I don't expect you to take that all first time through. You might have to go through it again, but it's actually, if you want to sit down and go through the math, then that's fine. If you want to go and I recommend you go to the internet and find a few other sources and read different ways of describing it, and eventually it'll sink in. It's not that you really need to know it, but it's just it's good to understand exactly how the process works. As I said, this is a two-step process, and what two-step means is that the sync packet and the follow-up packet came in two different packets. So the T1 went in the follow-up packet, and the one step is where it comes in the sync packet, which I think I have a slide on in a minute. Yeah, in fact, it's the next one. So here it explains a little bit more clearly. A one-step clock includes the timestamp in the sync message. So you see the one step on the left-hand side, and what that does is it just, rather than send a follow-up message, you send the actual time at which it was sent in the sync packet. If you think about that a little bit, that can be not as easy to do as you might think, because you need probably hardware support to stamp that packet as it's going out the PHY. So you've got to be a little bit careful where you put that timestamp in. So in some ways it's easier to do it as a one step, but sometimes you have to do the engineering to make sure it's accurate. Most of the other advantage to a one step really is around packet rates, because if you're sending 64 sync packets a second and you send 64 follow-up messages and you have 500 slaves, then obviously there's a lot of packets that are flowing. So that's really the main difference between the two. If bandwidth is an issue, then obviously one step's an advantage, but two steps is probably a little bit more accurate, but it depends on the engineering. Most of the network elements that our business unit, the service provider access group, has, when they're configured as masters, they're mostly one step. But of course, if you're a slave, you have to interact with both one-step and two-step masters. So it doesn't really matter whether you're a one-step master or a two-step master, because all the slaves have to listen to you anyway. So just to give you a look at the PTP packet samples, I've actually included a couple. This is a subset of the packet. I didn't include all the fields, but just to give you a flavor of what they look like. So you can see down the left-hand side I have a packet called the sync message, and on the right-hand side I have the delay request message, which are the two of the most important messages. So the sync message, you see it's this is based on IP UDP traffic, so you use port 319, and we have here a couple of fields I wanted to point out. So you'll see here there's a timestamp down the bottom, and there's two set parts to the timestamp. There's an origin timestamp in seconds, which is seconds since the epoch, which the 1st of January 1970. And then there is the nanoseconds, so it puts it in two different fields. So one is the number of seconds, and then it's the number of nanoseconds within the second. So this is based on the same sort of time system as Unix time, which is universal UTC. There's a slight difference, is that UTC has this concept called leap seconds. If you've not heard of leap seconds, then You can Google it, but you're opening a can of worms when you start looking at time. PTP doesn't have leap seconds. It uses what's called TAI time, International Atomic Time, and it always moves forward monotonically. It doesn't have the concept of leap seconds. So the PTP Grandmaster, for those who are interested, does actually understand the difference between UTC and TAI time, and it actually forwards it in one of these packets, in the announced packet, and you can then calculate UTC from PTP time. So it's sort of a minor detail, but there is actually a slight difference in there, which I know some people have asked about. Anyway, back to the sync message. So we have there, that's T1, that origin timestamp you see is T1. And the packet on the right hand side is the delay request. So this is the packet coming back from the slave towards the master, asking for a delay response. And you'll see here, this is the timestamp that it was sent. This is T3. You'll notice here that that seconds are quite a bit off from each other. So I don't know where I pulled these two different traces from, but it wasn't at the same time. Another thing I will point out is that there's a correction field. We talked about transparent clocks updating the correction field. Well, here's the correction field that can be updated by the transparent clocks. And so when we saw in the example where we were calculating T1 and T2, if you have corrections in there, then you're able to subtract the residence time from all the devices in the middle. If they're all transparent clocks, you can actually act as if they weren't there. So you can sort of take away all their residence time. So it can make a considerably better result if you have a lot of transparent clocks in the path. The other one is the response message from the master back to the slave, and what happens here, we have a delay response message, and again we have a correction field for transparent clocks, and here we have T4, which is the time that the master is sending the packet back. Now this just gives you some idea of what the fields look like and what's carried in some of these protocol frames. So some others, like the announced packet, if you're interested, it's quite straightforward to read the 1588 spec. The announced packet is sort of quite interesting because that's where the master goes and announces exactly what its capabilities are. It's sort of interesting as well, but I think just from the timing point of view, then these are probably the three most important messages. The next thing to come across is the concept of what's called best master clock algorithm, and best master clock algorithm has been it really introduces the concept of redundancy. I expressed earlier that the idea is to have minimal management operator overhead. We all want to reduce OPEX, and one of the ways that you do this is, of course, having redundancy for your clocking, and one of the ways you do this is by what's called the best master clock algorithm. And what this means is that the slave keeps track of a number of master clocks, and it determines which is the best master clock in the domain out of all the clocks it can see. So every ordinary clock, every slave clock or a boundary clock in a domain runs best master clock algorithm, and what it does is it's continuously monitoring all the master clocks it can see. And one of the advantages I expressed a little earlier when we introduced the concept of a boundary clock is that a boundary clock can switch between being the slave and the master. So where you have a boundary clock with a slave on one port and a master on the other, it can actually switch where the master becomes the slave becomes the master. BMCA is the thing that controls that. So it's a little like when you have a synchronous Ethernet ring. You have ESMC, which is telling you what your clock quality you're receiving. What it can do is it can reverse the flow of the timing information around the ring by where all the slaves become masters and the masters become slaves, if you like. BMCA does that. If a slave can't see a master clock, it something else on the node will become a slave, and then that slave becomes a master and passes the clocking on. I talked just about the PTP announce message. You can see here in this announce message I have just extracted a few fields from it, but this is the sort of information that's passed in an announce message, and the most important is with the clock class, which we talked about in part 1 of this series. There's a clock accuracy field, there's clock identity fields, and there's also information about where the source of time for this master comes from. So these messages are sent by the master so that the slaves can make a determination about the features of the master they're listening to and the quality of the master. Quite an important concept-based master clock algorithm. Again, profiles sometimes modify this. Profiles might say we don't want to use this mechanism, and we'll see a little bit later exactly that's what they do. Now, we talked a little bit about asymmetry and why asymmetry is a problem. And the reason is really because PTP assumes and has to assume that the delay in each direction is symmetrical, and that the delay from master to slave is half the round time trip. But as we've seen, there's a lot of things that can cause asymmetry. That's a physical world out there, so there's a lot of things about whether you're running copper and different lambdas go down fibers at different speeds of interfaces. There's all sorts of optical issues, just length of runs and links and so forth. All of those can introduce some form of asymmetry if you're not careful. So PTP can't measure asymmetry, so there's not much it can do there, but what it did do is it allowed you to correct for asymmetry if you know about it. And what this means is that PTP can have a correction field, be configured with a correction field, and then the PTP algorithms can use that correction field in its calculations. So it can actually correct for asymmetry if it knows about it. But of course you've got to know what the asymmetry is, and so that's not an easy process. The ways to do it, you can either estimate it, which is probably not that accurate, or you can measure it. And really what that means is you've got to plug a device into it, and you have to measure exactly what your offset is, and then configure that device to correct the PTP for that phase offset. Unfortunately, you have to do it for every path that could be used, and so that can get a little bit difficult because networks are dynamic. People change patch panels and replace cables, and things fail over, and routing protocols converge, and so it's very difficult to actually determine what every path could be, and then how you measure every path that you could take. That would be could be very difficult to do. The other thing, of course, as I said, you think this changes over time. So you might make temporary changes which cause the path to move, which would be one issue. But then, of course, over time things may change, permanently. So as I said, you could replace a cable or change a router, and so there could be some asymmetry from a device which disappears or appears. Some optical device could have buffering which changes over time, so a lot of things could change over time, so you might need to redo it. And obviously this is an expensive and slow task, and obviously a fairly significant OPEX. Only some PTP implementations allow configuration of this field. I know that some cell site manufacturers do have the ability to do this. We're looking to support it in our products. We already support it in a couple of products, so it is becoming more important, I think, as the larger service providers start deploying phase synchronization, especially to remote locations like cell sites. One good thing though in something like a cell site is that you don't actually have a lot of paths. You tend to have a very limited amount of routes back to the synchronization source, so it's not as bad as it might sound in a fully meshed type of network. So one thing we should talk about, we talked about with the physical frequency distribution and the whole concept of clock recovery. Similarly, with a packet-based network, we have the same ability. We talked about frequency in part 1, whereby you could have a reference frequency. Here I said a reference clock, but imagine this is a frequency coming in here. You have a packet master, you have a packet flow, you have a packet slave, and then at the packet slave you get clock recovery, and the clock recovery will then be used to condition the oscillator on that slave. So that was for frequency, but now we're talking about phase and time, and the same sort of thing happens. So as well as frequency being put into the device, you are now putting in time. So with time and phase, similarly that goes across the network, and at the other end you need to be able to use the time. Well, of course you might just require system time, but you might require the phase to go to a device, to a downstream device. And so what happens is there's a way to recover the clock, to recover the time of day, to recover the phase, and to put them out, and of course including a slight error which would have naturally come into it from running over the packet-based network. So to do that, you need some sort of interface and some sort of physical device that you can do that for. For frequency, it's quite easy. You can do it with SyncE, or you can do it with a TDM circuit. But you really need specialized pieces of hardware to do it for things like time of day and 1 pulse per second. So this, in the top right corner here, I've given you a picture of one of our pre-aggregation routers, the ASR 903. The ASR 903, you can see there, has a time of day input and output port. It can do both input and output depending which end of the chain it is. And it has a 1 pulse per second in if it's a master, and if it's a slave it has a 1 pulse per second out. Similarly, for GPS type environments, you can plug a GPS receiver to give it 10 megahertz in if it's a master and needs a reference, but also it's able to provide, if for instance a piece of equipment requires a 10 megahertz signal or a bit signal, it can give frequency out. So what I'm trying to do here is just say that when we delivered frequency, it was quite simple once you did clock recovery to distribute frequency at the remote location. Here, when you start talking about time and phase, you need an external timing interface which can actually plug into the equipment that needs the pulse or that needs the time of day. We explained a little bit about the formats of that time of day formats in part 1, so you can go back and review that. But basically it's a serial interface, and it just puts out a serial string of data indicating the time of day. And this is the this is a collection of some of the Cisco devices that that we deal with fairly frequently. As I say, this isn't all of them. This is really the one that's in my business unit, including the ASR 9000. But there's a lot of other devices inside Cisco. For instance, there's a whole series of industrial and enterprise switches which have similar capabilities. But just to give you an example of the current systems that we have. And so you can see here with the different colors in the top right hand corner, I have an ASR 901, which is a very small access router, typically used for deployments in places where you need very low power. It's environmentally hardened. Places like cell sites is a fairly typical example. And you can see there we have the interfaces for it, for the external timing interfaces. In the bottom left, we have our Metro Ethernet switches, the ME463800X. They don't have TDM interfaces, so they don't need some of this. Then we have at the bottom we have a ME2400CX, which is a Metro Ethernet switch with TDM, so it actually has all the interfaces. We have the ASR 903, which is a pre-aggregation router, and then we have the Edge router, one of the RSPs available for it, one of the switch fabric modules, which is RSP 440. So you can see here in all the different colors I've put in the different interfaces and the different types of data. So the first one I'll pick is the purple one, which is the bits interface here. Bits or SSU in ITU terms. And you can see that each of these devices can take bits in as a frequency reference. Now with the ME363800, really that's used to drive their SyncE, because they do synchronous Ethernet. They don't really need to understand PTP and phase, so really they're really just interested in a frequency source. These switches carry PTP traffic through them, but they don't really don't have the concept of understanding phase, and they don't need to then take phase in or put phase out, so they only have a bits interface. The rest of the devices, you'll see they have another frequency source, which is GPS sort of aligned 10 megahertz signal, which can come in from a GPS, or you can put it out to an equipment that normally has a GPS. And then we have the phase, 1 pulse per second, input and output. Here sometimes they use the one interface, but you can do both input and output depending. If you're the master, you take it in; if you're the slave, you put it out. Same with the 10 megahertz. And then you have a time of day interface, and the time of day interface is similarly, when you're the master, you take time of day in; when you're the slave, you put it out. So this just sort of to explain that you know, across a whole portfolio, you know, timing is a very important concept, and it's becoming very important for a whole range of platforms. It's no longer as specialized as it once was. It is now becoming, you know, required on a wider range of platforms. So that was sort of the situation earlier this year, but now of course we times have moved on, so I've updated this to show an example of a couple of new platforms that have shipped or are about to ship. And the first one is the ASR 920 series, and there's actually a range of products there in this portfolio, so I've only shown a couple. But again, you see we have, you know, the ability to do frequency-based sources in. We have the ability to do, you know, 1 pulse per second, and we have the ability to do time of day on both these platforms. The ASR 903 has 2 new switch modules. There's a RSP2A64 and a 128, which the 64 and 128 is their switching speed in gigabits per second. Again, like the RSP1, which preceded it, these are again have the 1 pulse per second in and out for phase, 10 megahertz for frequency, time of day for time, and bits for frequency. So you can see even you know, going forward, more and more platforms, it just comes as part of the portfolio that they need to support external timing interfaces. Now, I covered this in part 1. I'll just give it a quick repeat in part 2. I've here given an example. Again, we're talking about LTE, and this is really what has driven a lot of interest in the standards. Organizations over the last couple of years have rolled out quite a few standards to support telecom type applications. 4G network deployments are starting to require this stuff. So this is where a lot of interest has happened. But you know, there are other industries where this is important. We covered a little bit in part 1. You know, things like industrial applications. It's been important for quite some time for, you know, for robots and machinery, you know, to interoperate properly. Things like, you know, smart grids and things to handle, you know, power management of power systems and power distribution networks. We actually have quite a bit of experience in dealing with railways. The railways are interested in using phase for various reasons, for you know, for signaling and so forth. So there is a lot of interest in this area. But again, I'm just giving one example here of the LTE. In this case, we have to show that the cell sites are within plus or minus 3 microseconds of each other for phase. I explained in part 1 that, you know, one of the consequences if you don't get that right is if you're in a TDD network, which is a time domain duplex, where the uplink and downlink for a radio are on the same frequency, and you do it based on time slots. So every 100 milliseconds I'll transmit to the tower, and every next 100 milliseconds it'll transmit back to me. Now that all works really well, and then you go to the next cell site, and if that cell site doesn't have the same concept of when to start its 100 milliseconds and you transmit at the same time as it, then of course you'll drop the call. So each one of these scenarios of not getting it right actually has real consequences. So when they say they need 3 microseconds between cell sites, the reason is to make the service better for us. But that means for it to be, in this case 3 microseconds apart, that means we have to have every cell site to be plus or minus 1.5 microseconds. So if one cell site's plus 1.5 and the other one's minus 1.5, then there's our 3 microseconds. So it's now our responsibility to provide products to people deploying these networks so that they can do that, and really that's what's driving it. There is I'll show on the next slide as well. I've shown this slide before, but there's some work going on at the moment for what's like LTE Advanced, which is what a lot of people are talking about now, which is like the next generation of technology going into LTE. There are some in multiple techniques and services underneath LTE Advanced which are requiring phase. One of them is enhanced intercell interference coordination, and what this allows you to do is to deploy very small micro cells inside very large cells and not have them interfere with each other, which of course would have a lot of advantages, and that's sometimes you'll hear referred to as het nets. But as I say, it's not just an LTE problem. I mean, we also working with people like television distribution networks, so people that want to be able to broadcast TV, single frequency networks for digital radio and so forth, so that you need to have synchronization there. Otherwise your single frequency network doesn't work, which of course single frequency networks have a lot of advantages, that you don't use as much spectrum, and you can governments can take the spectrum back and reuse it for other purposes. So because it's so important, phase synchronization, we have to measure it. And how do we measure phase? So what we do is we take a reference signal, I've shown here as reference A, and we then take a test signal, so reference B, or you might have recovered it from another device. But basically this is the signal under test. And what you do is you compare the two of them and you figure out how far they are from each other. In this this example here, in one pulse it's plus 1 microsecond, in that the bottom signal's got a bit slower, and then it's minus 1 microsecond where it's sped up a bit. So in that case we define phase accuracy as the maximum deviation relative to the reference. So if you plus a little bit, minus a little bit, it's okay. It's really what the maximum you are away from what the reference is really what your requirement is, and that's what, when we say phase accuracy, that's really what we're talking about. So how do we test that? So I'll spend a little time just giving you a view of what a test environment would look like. Here we have on the left hand side we would have a 1588 master, and it would be sending a packet stream down a network, and you have some number of hops in the middle to your slave, which might be at a remote site, on a piece of equipment, or on a cell site or a transmission tower or something. And so what we have to do is we have to understand that when we're sending our PTP traffic is going through a lot of hops, we have to understand how good our phase accuracy is at the other end. And so this is what we're going to test here. So and really this is what you have to do. I mean, there's no guarantees about phase and time distribution. You really have to plug it in with the devices you have, and understand the latency, the PDV, the asymmetry that's in each of the devices you're going to run it across. and you really just basically have to test it and prove that it falls within your required phase accuracy. So this process is fairly common. Out of the box, you really can't assume that you're going to get the result that you want. So master and slave, then what you do, of course, is you need to put traffic over it. So you want to have a traffic generator that's representative of the traffic profile that you would normally run in your particular environment. So, if you're running, like television or video signals, or you're running, sort of power control signals, or you're running, railway signaling signals, you basically have a traffic generator which would put background traffic on the network to simulate a normal or a peak load that you need to understand. Because we have PTP sessions running, then between that, shown as a red and a blue, there may be multiple sessions running over it. So if you have more than one slave at the other end, then you may have more than one PTP session. And the PTP session is carrying two sorts of traffic really. It's carrying the frequency, they're shown in purple, and the orange, which is indicate the time and the phase. So you see we have a master here. The master is connected into say a GPS, and the GPS has of course a frequency source which it gives to the master. It may all be in the one box. This may be the one box. The actual GPS receiver may have a 1588 stack in it, which is fairly common. So that this would have an antenna from the GPS in here. I'll try and draw a GPS antenna. So you have a GPS antenna in here. It would have the 10 megahertz signal either coming out, or it would actually be the master itself and send the 1588 packets out, so it doesn't matter. And then you also have the 1 pulse per second information as well, so the 1588 gets generated. What you also do is you take a reference out of that same device. If maybe it's a SyncE reference, maybe they have an E1 bits interface or some forth, but there'll be some other interface on this primary reference clock, connected to the GPS. It'll have some other port. So what you do is you plug it into some sort of device that can do frequency verification. I said ANT20, it's a device not available anymore, but there's similar devices out there, like Calnox Paragons and so forth, that can do frequency verification. And what you do is you plug the reference signal into the reference port on this device. And then out here at the slave, you take, when your slave has done clock recovery and it has synchronized with the master and the oscillator settled down. So what you do is you take either an E1 port as an example, or a T1 port, or it could be a SyncE port, and you plug that into the test port on the device. And what the ANT20 then will do is do a frequency verification to make sure that how accurate the frequency has been maintained. Again, I covered that in some detail in part 1, so if you want more details back there, is the place to look. But what's different this time is we're now checking for phase and time of day. And the way we do phase really is, again, you use another piece of equipment. It couldn't be something as simple as an oscilloscope. You take a 1 pulse per second signal, a copy of the signal. You can put a splitter in it or something. Take a copy of the signal, put it into one reference port on the oscilloscope, and then from the slave you have one of those 1 pulse per second out ports on the slave, and you plug it into the test port on this device here, and it will actually count how many nanoseconds, microseconds, God forbid milliseconds it is you are from the actual reference phase. So that's basically how it's tested. So you start the master off. The slave will negotiate, synchronize with the master. That might take some time. I should point out that a slave to sync with a master can take, like 30 minutes. It can take quite a while, just because it needs to get enough traffic to be able to understand, exactly what the offset is and what the delay is between the master and the slave. So that's a completely normal process. It does take a while. And then once it's synchronized and locked with the master, then you'll be able to see the E1 and see that it passes the mask that you need, and the 1 pulse per second you'll be able to count, how many microseconds you are away from the reference signal, and then you can determine whether that meets your requirements that you need for your application. That's pretty much how it works, and that's sort of really the only way to know if what's going to if it's going to work for you. Now you're probably all in shock at seeing this slide, because it's a little bit busy, and so what I'll try and do is spend a couple of minutes just explaining what it is. As I said in part one, standards are a very important part of timing and synchronization, and although we have IEEE, which is a different organization, did the 1588 standard, the ITUT has become very involved in defining how to use PTP in telecom situations and in telecom applications. So, as I said, a lot of the work's gone on in this area in the last couple of years, both on the standard side and on the customers who are actually starting to get this equipment in, starting to test it, people like us who are starting to produce this equipment or equipment that follows these standards, and then big service providers who are starting to deploy it in their networks. So I'll spend a little time on this. So really the path to look for is the split into two here. So we have on the left hand side, going down the left hand side, we have what's called the frequency standards, and this is really about sending frequency over packet based networks, and these are the standards that are required to support them. On the right hand side you have phase and time. Now the frequency has been going the longest. It's the furthest along, so actually it has a lot more standards that have been fixed for quite some time. And in fact, we've been using things like SyncE, which is defined in these standards for many years now. So left-hand side frequency, right-hand side is time and phase. So just having a quick look at these standards, they have been, many of the standards are like for things like packet network limits, so they give you background information like 8261. They try and define network limits, 8261.1. So there are some basic aspects which give you background to the standard. And then they start to define clocks and different clock models. And the ones that have really had most work done on it up till now is the one in the red arrow here, which is 8262, and you should recognize that that's EEC as a synchronous Ethernet device. So 8262 is the definition of synchronous Ethernet, and it includes ESMC as well. As well as that, 8264, it's got SMC, sorry, so 8264 has the ESMC in it. So these running down the left hand side are sort of all known, they've been around for a while. What's started to be new though is profiles for IEEE 1588, and this is one here. This is the first one that was really done, which is G8265.1, and this is a telecom profile for frequency. So we'll talk a bit about G8265.1. It became fairly important a couple of years ago. A lot of people have been working on deploying G8265.1 and testing it, and I'll talk quite a bit about that in a minute. Then going down the phase side, we have a similar approach, and they give you some architecture, basic aspects, network requirements. So this is all happening up in this top section here. But we're talking about time and phase, and really what they decided now to do is to split it into two parts. And they've got what they call synchronization, time and phase again, with full support and with partial support. And we'll investigate what that means in a little bit, but full support basically means that the network hops in the middle, so between your master and the slave, are assisting you through some fashion to get synchronization from A to B. So this would be the case where, for instance, you have boundary clocks in the middle. So every node in the path between the master and the slave gives you some assistance for your PTP. Partial support has, doesn't have that. So they've sort of split it in that because 82671.1 you need full support. This would mean people have to go out and rip out their existing networks and provide nodes with every hop that understand PTP and can do something about helping PTP. Obviously that's not realistic, so 827.1.2 has some advantages here because a lot of people have networks existing and we have to take account of that. But anyway, 71.1 has been approved. 71.2 they're still working on. And then underneath that they define what's called the packet equipment clocks. Similarly over here we had on the left side where we had 8262 we had Ethernet equipment clocks. They have defined a packet equipment clock, which is if you like a packet version of SyncE. So for phase they've done the same thing, is that there's first of all they've defined the primary reference time clocks. So these are the things that provide the time of day and the 1 pulse per second. On the other side we only got frequency, but here they're talking about primary reference time clocks. And they introduced the concept of a telecom grandmaster, and we'll explain that a bit more when we talk about some of the profiles for telecom. And they've done the same for packet equipment clocks, so one's for the masters, one basically for the slaves. And then within that you have various types of packet clocks. So this is what's called a telecom grandmaster. There's a telecom boundary clock, there's a transparent clock, and there's a partial timing support for slave clocks. So these 4 different standards here are still really being cooked. 8273.2 has been done, but the other ones are still being worked on. But that's sort of just a bit of background. The other important one from 8265.1 for frequency is this one here for phase. So really why I highlighted those 3 with the red rings is like they're the sort of important ones to note. SyncE, PEC, telecom profile for frequency, and telecom profile for phase with full support. They're also working on one with partial, but that's still in draft form. So the situation that we're at the moment, you can see the 8275.1, this one here, is just been ratified. So we're all now working on making products that are going to fit that standard. This one's fresh off the press, it's just been printed. 65.1 we've actually pretty much implemented that across our product range, so that we're pretty much done with this. 8275.1 is the next one that we have to work on. So I wanted just to spend a couple of minutes talking about profiles. There's a profile standard built into 1588, if you like this, the default profile. So here across the top we have the 1588 standard, and if you want, this is the default profile. As we said, 1588 was originally designed around industrial solutions. And, version 2 extended that a little bit, but it was around industrial solutions, high-speed trading for very accurate time stamping and so forth for transactions. There was a version 1 and there was a version 2, and these are protocol versions. So I just sort of put this here for reference. And PTP modes is it includes like 1-way and 2-way. So you don't need 2-way if you don't need phase. You can get away with 1-way because you're all interested in frequency. 1-step and 2-step master clocks. So whether you produce a sync message with the time in it, or whether you do a sync message and put the time in a follow-up. PTP transport basically includes IPv4, basically all of them, layer 2, v4, v6. It has best master clock algorithm, and then it supports the delay request response for the 2-way to figure out the path delay. Node types they're supported is there's an ordinary master, there's an ordinary slave. Remember, there's a boundary clock that can flip between master and slave, and then you have a transparent clock. And the first telecom profile for frequency, the one on the left hand side in the previous diagram, was defined really for frequency transmitting frequency over a packet-based network, and that was required for really 2G and 3G mobile, which is really what drove it. They have found a version 1 of that's out, and what they did is they really took a little bit of a subset of the PTP that they of the whole standard. So it's a one-way or a two-way standard. You don't really need two-way, but most people do two-way. One step or two step, you have to understand both of those. It doesn't really matter. But the big change it was IPv4 unicast negotiation, and that's it. There's no other. There's no multicast. There's no IPv6. There's no layer 2. It's IPv4 unicast. And negotiation means that the slave basically asks everything from the master. So it asks for an announce message. It asks for, to be sent sync messages. It asks to be, it pretty much asks for particular services from the master, and the master will then grant them to it if it's able to. It doesn't use best master clock algorithm. It uses an alternate master clock algorithm. And what this does is, and the reason for this is it'll be explained in the next one, but the main reason for it is really you can define a local priority. The problem with best master clock algorithm is a little bit non-deterministic. So it just sits there and decides which is the best clock, and you don't really have a say over which clock it's listening to. A lot of service providers don't like that loss of control, so the alternate best master clock algorithm it's very much like we do with frequency. We can define the priority of our clocks. We can say we want to listen to this IP address as clock highest priority, next priority this IP address, third priority this IP address. So it allows us to define the order in which we want to use the clocks. Of course, if the clocks signal that they're no good, then we don't use it. We go to the next one. But the big difference is that you statically define which order you want to listen to the master clocks, which helps for things like when you want to provision, for instance, you have thousands of slaves. You don't want them all suddenly ending up on the same master, because of course it'll kill it. The other thing about telecom profile is there is no concept of there is a concept, but they do not use or specify a transparent clock, and there's no boundary clock. So if you put a network in according to telecom profile, then really according to that standard there's no transparent clock and no boundary clock. Now for transmitting frequency, that's sort of been fairly successful. But of course then they have to move on to phase, and that's where 8275.1, and it's sort of, I haven't filled out the form here, but this is the one here, 8275 for phase and time, and really it's been driven by 4G mobile RAN. And I've got a couple of slides on that in a minute. But just so you know, it's not just an issue with ITUT, the IEEE and different industries. So one is standard C37238, which is the power profile, and it's used for things like smart grids. And in smart grids, they're more interested in like industrial type approach, which uses a layer 2 multicast approach. They use BMCA. And they have the concept of ordinary master slave, boundary, and transparent clocks. So that's sort of how, just wanted to give you a flavor of what the profiles do and what sort of differences there can be between them. As I said, some of the fields can get interpreted slightly differently, or the values are only allowed to be this value and that value, and they've got to be fixed, or something like that can happen. So 8265.1, which was the first telecom profile for frequency synchronization over a packet network. So as we said, there was no boundary clocks, no transparent clocks, and that's what we mean when we say no on-path support. So this was for the simple reason that just about all of these networks did not have any form of device that understood transparent clocks or boundary clocks. Remember, transparent clocks need hardware timestamping, and you need PTP stacks and PLLs and stuff to be able to run PTP. So there's hardware required. It's not something you get for nothing. So they really required something that would fit their existing networks, and so the PTP just got carried as IP traffic through interim nodes. and that's why they adopted IPv4, UDP, IPv4. One thing they did do, and I did cover this in part 1, was about the PTP announce message carries the quality level, the quality levels that come from SSM, that come from SyncE, ESMC, and that are all defined in G781. And if you want to see, I did give some slide or two in part 1 on the way that we distribute the traceability of clock quality levels through a network, and the PTP announce message was used in G80to65.1 to interoperate with that, so that you could you move between TDM and packet-based timing. It used unicast. Clearly it was just IPv4 unicast, again negotiation model. BMCA was not adopted. It was replaced by, as I said, a static provisioning, and what this allowed service providers to do was to be much more planned about which slave would be configured with which masters. So that allowed them, because they had such very large numbers of devices, that they could, do being able to share the capacity and properly plan the capacity of their masters. They also got rid of the idea that BMCA could switch a port from a master to a slave, and in a boundary clock this is. So if a boundary clock that has a master and a slave on the same device, well, and they could flip backwards and forth under BMCA control, well, they got rid of that for a telecom profile. It's statically configured. So once you define a master, it's a master, and once you define a slave, it's a slave, and it can't change back to a master, even if something else on the machine is getting the signal. And the other thing they did too is that there was a telecom profile certification process that's been defined to ensure compliance. So it doesn't actually measure the clock quality. What it does is it measures your compliance to 1588 telecom profile. So when you say you're going to send 64 packets a second, do you actually send 64, or do you send 63, or do you send 65? You're allowed to send 63, you're not allowed to send 65. So there is actually a compliance that actually determines whether you've answered every response correctly, if you behave correctly given particular series of packet flows and events, and also make sure that you're translating properly between all these quality levels. So far we have actually gone through this testing process. The ASR 903 was the first device to pass this test, and it's called the IEEE certification ICAP, I think, program. And so at the moment we have the only device that's passed that. 80to75.1 is for time and phase transfer. So this is the equivalent for phase, not frequency. This was recently approved in April. And it's a little bit different to the frequency telecom profile, in that it requires full network assistance, and it doesn't allow transparent clocks. So what this means is you pretty much have to have every node between the slave and the master has to be a boundary clock. So of course this is not very helpful if you have a string of devices that don't have the capacity. You basically have to rip them all out and replace them. So really it's a hop by hop distribution model, in that every node is a slave to the master next to it, and so you get chains of boundary clocks together, with every node having to be a boundary clock, no transparent clocks. And the other thing too is there's no VLAN tagging as well, so it's all without VLAN tags. They also recommend, we talked about hybrid clocks, they also recommend using a physical layer frequency, so using the PTP just to transmit the clock phase and time, and using SyncE or something to be able to transmit the frequency at the same time, because this gives a lot better results when when you're going into holdover, and just the stability of frequency is just so much better. It makes phase results a lot better. So because your frequency is so much more stable, your results on phase distribution actually work a lot better. So it's recommended. But of course, this means not only do your devices now have to support telecom boundary clocks, they have to also support synchronous Ethernet as well. So they actually did define some new concepts or some new names for these devices. You can actually see I put the acronyms at the bottom, but there's a telecom time slave clock, which is basically an ordinary slave. There's a telecom boundary clock, and there's a telecom grandmaster, and there's a few differences between them, but what they're saying that for the telecom slave clock, which is the slave, and the boundary clock, frequency synchronization is recommended, and also for use in holdover. For 82751, the mapping is Ethernet. So they've taken Annex F, which is one of the annexes of IEEE 1588, and it shows you how to map PTP onto Ethernet, and that's what they've chosen to use. So it has to be Ethernet, cannot be IP. So it's not routed at all. And if you've got chains of devices connected to each other, it's probably not a big problem, because it's all point to point. The transmission is all multicast. They have two multicast addresses, one's forwardable, one's not forwardable. You need to be able to interact with both. It has to be two-way. You need to send the traffic forward and back, because we need to determine the delay, because we need phase. For your frequency only, you could get away with one way, but no, this needs two-way. Of course, we also need to interoperate with 1- and 2-step masters. It also uses alternate BMCA. Similarly to 8265.1, it does not use the best master clock algorithm, so it allows you again to statically define things. There's a slight difference, is that you have this concept of a telecom grandmaster, and a telecom grandmaster can consist of both an ordinary clock, which is master only ordinary clock, it's not allowed to change, and it can be a master only boundary clock, so the master side of a boundary clock, and that's what's called a telecom grandmaster. But normally the state on that grandmaster cannot change. Then for the slave clock, it's the same. The state is static, so both the time slave clock and the telecom grandmaster clock, they do not change state, but the telecom boundary clock can change state from master to slave and back again, much like we saw with the original 1588 profile. Again, this is sort of required, I suppose, for chains and rings, where you might need to move from being a slave to being a master if the direction of flow of timing information moves the other way around the ring. The other one that I'll just cover really quickly, 8275.2, is for phase and time transfer without support in the network. So this will not be a chain of telecom boundary clocks. So this is still work in progress. The drafts, there was a draft in June, and a lot of it's still up for discussion. But again, this is where you have intermediate nodes that don't know about PTP. So it's more useful in environments where people already have existing networks. In this case, they used IPv4 mandatory, or Annex D from 1588, and Annex E, which is IPv6, is optional. They're still talking about IPv6, but IPv4 is definitely mandatory. It's unicast negotiation only, which is again like phase, again like the frequency telecom profile 8265.1. Mode is one-way or two-way. They're a bit more flexible here so far. They say you only need two-way if you need it. So if you only need frequency, you can go to one-way. But of course, this is a phase, so you probably need two. Again, you need to interoperate with a 1- or a 2-step slave. Again, it uses alternate BMCA. It doesn't use the dynamic BMCA from 1588. So again, you define the order in which you want your masters to be consulted, or which ones you want to use. I'll show you in part 3 the configuration to do these various options, so you'll be able to see there where you configure the order of possible masters. Again, we've also got this, don't have this concept of dynamic switching. Masters are masters, slaves are slave. There's no switching between them. So far they've only talked about ordinary clocks. They're still talking about boundary clocks and transparent clocks. I think the thinking now is boundary clocks are most likely to be included, but transparent clocks, I think the jury is still out, as they say. I'll just do some quick deployment considerations just to show you a range of our products. The ASR 9000 is, well, the latest reorg is now in my business unit, but 7600, just to give an idea, this is, I really just will click through this because this is really about SyncE and TDM to show that pretty much they support all clocking and timing, and these devices are all telecom devices, and so they've supported this stuff for years, or certainly since the devices were first produced. So yep, they do frequency distribution. For frequency and time distribution with 1588, what I have here just collected a piece, sort of a subset of the information. I tried to make sure it was accurate as possible. What we have is ASR 9000 supports ordinary master, slave, boundary clock. 7600 the same. They all really support most of them. The green tick really is to show that 8265.1 telecom profile has been supported, so it's supported across all those platforms. The 7600, I don't actually have the latest up to date whether it supports it or not, but yeah, it may do. I wasn't able to find with a quick search, but certainly the other ones do. One more thing I should point out, of course, that this is not a Cisco-wide portfolio, so this is just in the service provider sort of space. So there is actually quite a number of other platforms that support 1588 in the industrial area, industrialized ruggedized switches and so forth, that also support even things like power profile and different profiles. So, but talking about the telecom and the service provider space, this is sort of the range that we currently offer. So I've just put this in really as a little bit of reference, just to show you where the support is up to in those products. So I was just really talking about in a little bit more detail. Synchronous Ethernet, ESMC, and G8262 from Synchronous Ethernet. So support input, output. Sometimes it's they take input on the NNI ports and output on the UNI, but basically Synchronous Ethernet. Adaptive clock recovery tends to be not supported anymore. It's sort of an old way of doing things. It's quite limited. Ordinary clock, master clock, and boundary clock. The ME3600 are Ethernet switches. They don't have hardware to do PTP. They're mainly the Synchronous Ethernet world. Of course, they can switch PTP traffic without any problem. Line clocking, of course, anything with TDM needs to support that. Best master clock algorithm. So the 3600 and the 903 support best master clock, and they also support the alternate best master clock. The 901 doesn't support best master clock because of its deployment scenarios. It doesn't really have to. It needs to support the 8265.1 alternate best master clock, which of course is supported on the other two as well. Support for transparent clock, again, and 901 hardware limitations. It's not supported on that, which is not really that surprising because it's normally at the end of a chain. It's not halfway through the middle. Hybrid clock supported on everything, boundary clock supported on everything. Telecom profile is reported on everything. Actually, VRF aware PTP is supported on the on a lot of them as well, and that means you can put PTP in a VRF. PTP over Ethernet is supported in unicast on the 903, multicast on the 901. not currently supported on the 3600. I'll put a comment down if I find out the date that that's going to be delivered. And the ability to configure the delay asymmetry. So this is where you have a phase offset because of asymmetry. We're actually looking at doing that now. It's going to be supported in the 901 in November, and we're looking at it for the roadmap for the other two platforms. And just point out that telecom profile support there for the 3600 24CX is shipping. So that shipped in 3.13, which was came out in July. So that's slightly outdated. So we have a clean sheet there for support for a telecom profile. I thought that was wrong, so sorry about that. That's actually supported as well. Just to give you an example of the sort of testing that we have to do to actually see all this equipment works properly together and it actually delivers what people are looking for and we get the result that we designed for. We have actually gone and done quite a bit of extensive testing that and we're constantly undergoing it all, repeating it all in different environments with different profiles and different hardware configurations. This gives one example we did a couple of years ago with the 903, was a little bit younger, and we did, for instance, a multi-hop test with just using transparent clock, and we put 30 nodes together using just transparent clock. And then what we did is we changed a couple of them with transparent clock and made one or two of them boundary clocks. And then we did multi-hop tests with 20 nodes where we just had one or two boundary clocks, which is which is a fair bit when you don't have any support. You just got one or two boundary clocks, like every 7 or 8 nodes to clean up the noise. But they all passed all their TDEV and MTI masks, so we passed all that. So if there's any issues we would have found, of course, then we went off and fixed them. But this just gives you we sort of do this testing across a whole range of products. But this is one example, and just to show you what that looks like, I sort of included a picture here from one of the test plans. And you can see here we have a PTP Grandmaster. In this case, it's it looks like a Symmetricom TP5000 or something. It has a GPS antenna into it, and what it does is it gives a reference signals out. So we have reference 1 pulse per second, which goes into an oscilloscope. We have the reference frequency, which looks like goes into a Calnex. And so they're used as the two reference frequencies in the test equipment. And what we do is we have the PTP, this Symmetricom Grandmaster has various options. It's also the PTP Grandmaster. So these are dedicated platforms that can be a master. We do quite a bit of work with these and other Grandmasters. And what we did is we feed PTP stream in through this ASR 903 here. And pretty much what it does is traffic flows all the way through these 30 nodes, all in a big long list here, until it comes here, and this is the PTP slave. So the traffic has gone through each one of these devices. They're all hooked together in a chain. That'd be too easy. What we also do is we put this Ixia in here, which is a traffic generator, and what we do is we just pump traffic right through the network at the same time. And I think we were running 80% boundary traffic at the time of this test. So this gives you the sort of idea of the testing you have to do, and the idea then is that you have the Grandmaster, the slave gets configured, it negotiates with the master, comes up, you wait until it's locked, and then you check that the recovered frequency meets the mask that we talked about, and then you check the 1 pulse per second, and you check how much how much phase is shifted because of that. Now, there's actually quite a deal of reports which we have to write up in white papers and so forth, but that sort of gives you the idea of the testing we go through to make sure this stuff works. So just in conclusion, what I wanted to just give you an idea of sort of what's hot in clocking this year. It's sort of it's a view sort of from the space that I'm involved with anyway. So 8265.1, that's done. As I said, all these platforms support 8265.1. We have done IEEE ICAP certification for the 903. It was the first device certified. There's probably a press release out there somewhere you can read. There'll be many more, and that's an extremely rigorous process. I know because I did it myself with the test organization, and they are absolutely extremely pedantic in making sure all this stuff works really well, and it's a really good process to go through to make sure everything works well. So yeah, and we're we see now that it's very good for us because we're able to show that we absolutely have met the standards, and we have all the test cases and what should happen to prove it. So that really helps us if we have any interoperability issues. We can start to see more PTP over Ethernet. We're looking at supporting smart grid industrial applications. So PTP over Ethernet support is coming. There's support for PTP over MPLS, being able to deal with PTP and with MTLS labels. But of course the thing that's probably of most importance is the 8275.1 and 8275.2. So full support for telecom profile. So now the standards are done for 8275.1, then we're all thinking and engineering, scratching their heads and getting their pencil sharpened to figure out how we do this. Of course, we started a little while ago, but now it's becoming a rush. Also, they're interesting to see how the standard goes with 8275.2. So I think 8275.1, maybe people don't realize that you need to have boundary clock at every point of the path. So maybe that won't be as enthusiastically adopted as many think, but certainly 8275.2 will probably be widely deployed. As people are deploying now, because phase is starting to get deployed, people are asking for special features for be able to support phase deployment. So special tools, and when you deploy this across a large number of sites, you might figure, well, it'd be nice if we had this feature. So we're working with customers already to do some of this. One feature we're sometimes asked for is cross VRF BC support. So this is where you have the master in a boundary clock, the master's in one VRF and the slave's in another. I don't know whether this is really a requirement, but certainly we've a few people expressed interest in it, so we'll see what's required to do that. So key takeaways, as we've seen before, we're talking about synchronization having three aspects. Frequency we've covered in part one and partially here, but really we're looking at phase, and it's increasingly required. And time, of course, has always been required in a lot of applications, but the increased accuracy is what's driving some of this. So for things like you said, high frequency trading and so forth, or even things like us, measuring services and stuff, you need to be able to go to well under a millisecond, and in some cases down into the hundreds of nanosecond range. The need for synchronization is growing. There's more applications every day that it's relying on it. Mobile networks is top of our mind at the moment, but industrial solutions, transport solutions, transmission, broadcasting, smart grids, high frequency trading. There's a lot of things that are driving various aspects of synchronization. And we've seen certainly the interest in phase synchronization over the last year is just grown exponentially. The big thing we're sort of taking away, especially with things like hybrid mode, is do physical distribution with where you can. So if you've got SyncE, use it, and if you need phase, put 1588 over the top of it, and use the hybrid mode where you use SyncE for frequency. Phase is using PTP, and if you can't do SyncE, then you use packet-based frequency. But you have to be aware of what that requires. From a point of on-path support, the fact that you've got your quality of service, the fact you've got priority queuing, the fact that your background traffic is managed, that your packet delay variation, your asymmetry, and all those things are understood. And then pretty much you have to test it to make sure it does what you want. And as we've seen, 1588 allows profiles to create the various use cases. Default profile is originally around industrial solutions, high frequency trading, so forth. Service providers for 8265.1 for frequency, 2G, 3G networks. Now 8275.1 for 4G networks, mobile service providers. Power profiles is as well been around for a while. And that is end of part 2. And thank you very much for listening.